Hi, I'm Irma. Today we're talking about a system being in equilibrium. What does it mean for a system to be in equilibrium? It means an object is either standing still or it is moving at a constant velocity. Moving at a constant velocity. Yes, a car that is moving at 60 kilometers an hour and it keeps that speed is a system that is in equilibrium. What does it mean for a system to be in equilibrium? It means that the net force on the system will be equal to 0. Not that there's no forces acting on it, but it means that if I add all my forces together, the total of all my forces will be equal to 0. A car traveling at a constant velocity is in equilibrium. Let's have a look at all the forces that acts on a car while it is traveling. That dot represents my car. I've got a force acting downwards. The force that the Earth exerts on an object, that is called your gravitational force. I've got a force that the surface of the road exerts on the car. That is called your normal force. Of course, the engine exerts a force on the car. We talk about that as F applied. And the engine of the car exerts a force against friction. I need to overcome friction when a car is driving. For the system to be in equilibrium, my normal force must be equal to my gravitational force. And my applied force, the force that the engine exerts on the car, must be equal to my frictional force. Let's have a look at another example. I've got an object hanging from the roof. I've got a gravitational force acting on that object. We call that my gravitational force. There's a string attached to the roof, and that string is exerting a force upwards on this object. I'm going to call that tension. And then I am pulling this object sideways. In other words, that is my force applied. The object is standing still. So these three forces are in equilibrium. When I add them together, they're going to have a net force of 0. What can I do with these three forces? I can take these three forces and move them in such a way that when they follow head to tail, they will form a closed triangle. What am I going to do? I'm going to take FG and I'm going to move it this way. So I'm going to put FG over there. I'm going to take tension and I'm going to move it backwards. So let's draw the final diagram for this object. I'm going to have the applied force acting this way. The gravitational force is going to act downwards and the tension in the rope will close this triangle. This is my force. The tension in the rope then will close the triangle. Again, look, I've got 90 degrees over there. If the force applied is going to be 4 newtons, and my gravitational force is going to be 3 newtons, what will the tension in the rope be? Yes, you guessed right. It will be, again, Pythagoras, t squared equals 4 squared plus 3 squared. That then gives me a value of 5 newtons. And again, what will my angle be? My angle theta, yes, I use tan theta. Tan theta is my opposite side, 4 divided by 3. And that gives me an angle of 53,3 degrees. Now, how does my tension in my rope, that is called the equilibriant, How will it differ from my resultant? If I've only had the tension in the rope, or the force in the rope F, going this way, and my gravitational force going down, my resultant would have been from the beginning of the first to the end of the last. I would have got exactly the same value, 5 newtons. 4 newtons, 3 newtons, I use still Pythagoras, and my resultant in this case would be again 5 newtons. But where will my angle be in this case? My angle will be over there. And my angle tan theta will be, in this case, opposite 3 divided by 4. And I get my angle as 37.7 degrees. What is the differences between my resultant and my equilibriant? They've got the same size. They've got the same size. But if you look at this picture and this picture over here, that my equilibriant goes this way, that is my equilibriant, and my resultant goes in that way. In other words, they are in opposite directions. A resultant is the sum total of 2 or more forces. My equilibriant is the force that keeps all the other forces in equilibrium. Thank you very much for listening to this lesson.